Lesson 22.1, Data Gathering Techniques. Essential question. Under what circumstances should a sample statistic be used as an estimator of a population parameter? The statistic, let's see here. The statistic needs to come from a representative sample. Which is most likely to be obtained and the sampling method includes randomness. And the sampling method obtains or involves randomness. All right. Finding the means of samples obtained from various sampling methods. You collect data about a population by surveying or studying some or all of the individuals in the population. When all the individuals in a population are surveyed or studied, the data gathering technique is called a census. A parameter is a number that summarizes a characteristic of the population. When only some of the individuals in a population are surveyed or studied, the data gathering technique is called sampling. A statistic is a number that summarizes a characteristic of a sample. Statistics can be used to estimate parameters. Consider the following table, which lists the salaries and thousands of dollars of all 30 employees at a small company. In this Explorer, you will take samples from this population and compute the mean of the sum of the data divided by the sample size. Okay, so let me make this a little bit smaller, and we'll say 125. That gets them all on there. All right, good. Suppose the employees whose salaries are 51, 57, 58, 65, 70, and 73 volunteer to be in the sample. This is called a self-selected sample. Compute the sample's mean, rounding to the nearest whole dollar. So the mean will equal, and then we're going to add those numbers up, 51 plus 57 plus 58 plus 65 plus 70 plus 73. And then we're going to divide it by the number of numbers that we have. We got 1, 2, 3, 4, 5, 6. So we're going to divide that by 6. And let's see, add those up. That's 374 over 6, which is about 62. Suppose the 6 salaries in the first two columns of the table are chosen. This is called a convenience sample. So we're going to just take these 6 right here. All right. Record the salaries and then compute the sample's mean, rounding to the nearest whole dollar. So we've got mean equals, and that's 21 plus 24 plus 44 plus 46 plus 58 plus 62. Again, we've got 6 numbers. So we add all of those up and we get 255 divided by 6, which is about 43. All right. Now, suppose every 5th salary in the list is taken. Reading from left to right, in each row is chosen. This is called a systematic sample. So every 5th one. So let's see, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. That's going to give us 50, 57, 64, and 80. All right, so the mean will equal 30 plus 41 plus 50 plus 57 plus 64 plus 80. And again, that's 6 numbers, so we'll divide it by 6. And that's going to be about 54. Notice we took 3 samples from this data. We took 3 samples from these numbers here, and 1, 2, 3, and we came up with 3 totally different means. Huh. All right. So D, label the data in the column with the identifiers 1 through 10 for the first row, 11 through 20 for the second row, and 21 through 30 for the third row. Then use a graphing calculator's random number generator to generate 6 identifiers between 1 and 30. As shown, if any identifiers are repeated, simply generate replacements for them until you have 6 unique identifiers. This is called a simple random sample. Record the corresponding salaries and then compute the sample's mean, rounding to the nearest whole number. Okay, so how do we do this in the Inspire? In the Inspire, go to Calculator, and then that's Menu, and Probability, 5, 4, and then 2. Menu 5, 4, 2, and then 1, 30. And then, of course, you can go up there and grab it and do it again. And go up there and grab it and do it again. All right. Now, for simplicity, I'm going to use these generated right here. So what did we get? Let's see here. And I'm going to need a different color, so I'm going to use green here. Mean. So the mean, and then we got to, what are those 6 numbers? 28. What's the 28th number? Let's go back over here to look. 28. So that's 10, 20, 1, 2, 25, 26, 27, 28. So we got 71. 71. And then 5. 5. That's 30. 71 plus 30 plus, I'm not going to be able to read them. Let me lower this down some. 71 plus 30. And then 16. So let's go to 16. So that's 10, 15, 16 is going to be 51. Plus 51. 13. So it's 10, 11, 12, 13. It's going to be 47. 23. 23. So that's 10, 20, 1, 2, 3. That's 62, and I think 2 was the last one, 24. Yeah. Plus I forgot what it was. 23 is 62 and 24. 62, 62 plus 24. 24. And then and divide that by 6. And what do we get? So we got 71, 30, 51. So control divide 71 plus 30, 51. 30 plus 51 plus 47 plus 62 and 24. 62 plus 24 over 6. And that's going to give us 95 halves. Control, enter, 47.5. So that's going to be 47.5. So that's the mean. Notice the difference. You got 47.5. You've got 62, 43, and 54. Compute the mean of the population, then list the 4 samples from best to worst in terms of how well each sample mean estimates the population. All right. To do it in your calculator, the easiest way is to go to the spreadsheet, and then we'll just kind of put them in there. Let's see, we got 21, 24, 26, 28, 30, 32, 33, 35, 37, 41, 44, 46, 47, 49, 50, 51, 52, 54, 55, 57, 58, 62, 62, 64, 64, 65, 70, 71, 73, and 80. All right. Make sure you put your number, and we'll just put we'll put salary here. Salary. All right. Now, how do we connect? How do we calculate? Make sure you got it in the thing, and then menu 411. Number of lists is 1. We call it salary. All right. So we're looking for the mean. The true mean is 49.366. 49.366. So let's see here. 40. So the mean the mean is 49.366. And we'll just say 49.4. All right. Then list the 4 samples from best to worst and how well each sample mean estimates the population mean. So this is 47.5. So, and that was by simple random. Simple random came in close. And then let's see here, 43 and 54. So that's 6 away, and that's 5 away. So this right here was systematic sample, and then convenience. So systematic, and then convenience. And then the last one was self-selected. self-selected. All right. With the way the table is organized, both the convenience sample and the systematic sample have means that are not too far from the population. Why? Well, the reason why, let's see, the systematic and the convenience. What did we do for convenience? Let's go back and look. What did we do for convenience? We just took these right here, right? Just took those right there on the end. But notice it is in ascending order. Okay, so that got us two at the very beginning, two at like the 1/3, and then two at the 2/3. So that kind of helped. And then what was the other one? And convenience and the systematic sample. Systematic sample. Let's see. Systematic. We took every fifth one. So notice here we got at 1/6, at 2/6, at 3/6, at 4/6, at 5/6, and then so that's why they actually did pretty well. Okay, but the one that got the closest really was the simple random. Okay, and that's it. It does that every single time. So the data. Let's see. The data are arranged in ascending order. All right. Now, do you think that if they was not arranged in systematic order or ascending order, that they would have done as well? Maybe, maybe not. All right. Distinguishing among sampling methods. The goal of sampling is to obtain a representative sample because the statistic obtained from the sample is a good estimator of the corresponding population parameter. Some sampling methods can result in a biased sample that may not be representative of the population and can produce statistics that lead to inaccurate conclusions about the corresponding population parameters. Sampling method, simple random sample. Each individual in the population has an equal chance of being selected. Self-selected sample. Individuals volunteer to be part of the sample. Convenient sample. Individuals are selected based on how accessible they are. Systematic sample. Members of the sample are chosen according to a rule, such as every nth individual in the population. Stratified sample. The population is divided into groups, and individuals from each group are selected, typically through a simple random sample within each group. Cluster sample. The population is divided into groups. Some of the groups are randomly selected, and either all the individuals in the selected group are selected, or just some of the individuals from the selected groups are selected, typically through a random sample within each selected group. The explorers showed that simple random samples are likely to be representative of a population, as are other sampling methods that involve randomness, and are therefore preferred over sampling methods that don't involve randomness. Identify the population, classify the sampling methods, and decide whether the sampling methods could result in a biased example. Explain your reasoning. So A, I'll let you do A, and when you get back, we'll take a look at B. All right. So B, administrators at your school want to know if students think that more vegetarian items should be added to the lunch menu. A, the administrators survey every 25th student who enters the cafeteria during the lunch period. So A, This is a systematic sample. Systematic sample because the rule of every 25th student is used. The rule of every 25th student is used. This method isn't likely to result in a biased sample. Isn't likely to result in a biased sample because a wide range of students will be surveyed. Will be surveyed. All right. B, the administrators survey the first 50 students who get in the lunch line to buy lunch. So this is a convenience sample. Because the students are easily accessible. This method, I'd say, is likely to result in a simple bias sample because, well, one, it does not include students who bring their lunch. All right. C, the administrators use a randomly generated list of 50 students from a master list of all students. Okay, this is a simple random sample because each student has an equally likely chance. Each student has an equally likely chance of being chosen This method isn't likely to result in a biased sample because the students are chosen randomly. All right, good, good. Your turn. Identify the population, classify the sampling methods, and decide whether the sampling methods could result in a biased sample. Explain your reasoning. So, 3, a local newspaper conducts a survey to find out if the residents of the city think the use of handheld cell phones while driving in the city should be banned. A, the newspaper sends a text message to a random selection of 1,000 subscribers whose cell phones are listed in the paper's subscription database. All right, so let's see. Identify the population. The population would be all adult residents of the city. So the population is all adults residents of the city. Decide whether the sampling methods could. All right, so A, the newspaper sends a text message, which a simple random sample of subscribers with cell phones. Everyone has an equally likely chance of being chosen. Likely to be biased because not everybody has a cell phone. So that's a simple random sample. Simple random sample. All right. That is a simple random. Now, could it result in a bias? Yes, it does, because biased because everyone does not have a cell phone. I know y'all are thinking that, but that it might be hard to believe, but actually everybody doesn't have a cell phone. Uh, or do you think everybody gave their cell phone number to the newspaper? Maybe, maybe not. And they are left out of the survey. What about B? Using the 10 neighborhoods into which the city is divided, the newspaper randomly contacts 100 adults living in each of the neighborhoods. Okay, so B, that's a stratified. That's a stratified sample. All right. Individuals are grouped, and a random sample from each group is selected. Not likely to produce a biased sample. Well, want a wide, 100 from each of the 10 neighborhoods, so you're getting a bunch. Making predictions from a random sample. In statistics, you work with data. Data can be numerical, such as heights or salaries, or categorical, such as eye color or political affiliation. While a statistic like the mean is appropriate for numerical data, an appropriate statistic for categorical data is a proportion, which is the relative frequency of a category. Example 2. A community health center surveyed a small random sample of adults in the community about their exercise habits. The survey asked whether the person engages in regular cardio exercise, running, walking, swimming, or other, and if so, what the duration and frequency of the exercise are. Of the 25 people surveyed, 10 said they do engage in regular cardio exercise. The table lists the data for those 10 people. Calculate statistics from the sample and use this statistic to make predictions about the exercise habits of the approximately 5,000 adults living in the community. So y'all go ahead and do A, and then when you get back, we'll do B together. All right, B. Calculate the mean duration of exercise for those who get regular cardio exercise and the mean frequency of exercise for those who get regular cardio exercise. Use the mean to predict, for those who get regular cardio exercise, the number of hours spent exercising each week. Show your calculation and include units. Mean duration of exercise for those who get regular cardiovascular exercise, that's going to be 48 minutes. All right. Mean frequency of exercise for those who get regular cardio exercise is going to be 3.7 times per week. 3.7 times. To predict the number of hours spent exercising, multiply the mean duration of exercise in minutes for those who get regular cardio exercise by the mean frequency of exercise in times per week for those who get regular cardio exercise. This product will be in minutes per week. To convert to hours per week, also multiply by the conversion factor 1 hour over 60 minutes. So the predicted time spent exercising is 48 minutes. 48 minutes. 3.7 times per week. Okay. Is approximately 3 hours per week. Scratch out the minutes. Okay, and that leaves you hour and week. And 4.48 times 3.7 is 3 hours. Number 4, discussion. How much confidence do you have in the predictions made from the results of the survey? Explain your reason. The sample was random, which makes the results representative of the population, but the sample size was small, which may not make the results accurate. The sample was random, which makes the results representative of the population. But the sample size was small. Which may not make the results accurate. So it needs to be representative of the population, and it also needs to be of a sufficient size. Number 5, your turn. A ski resort uses the information gained from scanning season ski passes in lift lines to determine how many days out of each season the pass holders ski and how many lift rides they take each day. The table lists the data for a random sample of 16 pass holders. Calculate the mean number of days skied and the mean number of lift rides taken per day. Use the means to predict the number of lift rides taken per season by a pass holder. Okay. So the mean number of days skied. Mean number of days skied and so we would add all of these up, and then 1, 2, 3, 4, 5, 6, 7, and divide by 16, and you're going to get 12.125. And the mean number of lift rods taken per day. All right. Now we're going to add up all these bottom numbers and divide them by 16, and we're going to get 11.625. Okay. So the predicted number of lift rods taken by a pass holder per season is 12.125 days. So we've got, all right. So let's see, the predicted number of lift rods of lift rods. Okay, predict the number of lift rods. So we're going to have 12.125 times 11 point, let's see, 12 a day times 11.625 lift rods, and that's going to be per day. And so days going to cancel out, and we're going to get 12.125, and that was supposed to have been 11 points. That's 11.625, and that's going to give you about 141 lift rods. 141 lift rods. All right. Name a sampling method that is more likely to produce a representative sample and a sampling method that is more likely to produce a biased sample. Simple random sample is more likely to produce a representative sample. So one of the best is the simple random sample. Is more likely to produce a representative sample, and a self-selected sample is more likely to produce a biased sample. All right. Why are there different statistics for numerical and categorical data? Numerical data are numbers that can be ordered to find the median, sum to find the mean, and so on. Categorical data are categorizing, and you cannot perform operations on categories. Think about it. If you add up all the different zip codes in this area here, and then you divide it by the number that there are, you're liable to get a zip code that's not even around here. Same thing. What if we'll just say we'll let blue eyes be 1. We'll code that as a 1. And brown eyes as a 2. And we'll say green eyes as a 3. Okay, so we do that for each student in here, then we add them all up and divide by the number of students in here, and we get something like 2.7. Well, what sense does that make? What sense does it? I mean, part of his eye is brown and the other part is green. Okay, so that's why you can't find a mean or a median for a categorical data, because it doesn't make any sense. Now, if you did all this up and you found that 23% had blue eyes, 47% had brown eyes, and that's 6, 7, and 30% had green eyes, that would make some sense. Okay, so that's why. Essential question check-in. Explain the difference between a parameter and a statistic. A parameter, and they're sort of like the same thing, but they're different. Okay, and the reason why they're different is one refers to something that the other one doesn't. And what I mean by that is a parameter is a number that summarizes a population, is a number that summarizes rises. A population. And a statistic is a number that summarizes a sample. Is a number that summarizes a sample. A sample taken from a population. All right. And to get a parameter, you have to do a census. You have to do a census to get a parameter. And a statistic is from a sample from a population. All right, great job, folks. See you tomorrow in class, and y'all have a great evening.